Okay, yeah. I forgot to record, so here we are recording. But I didn't really miss much in the recording because we were just going over homework problems. Okay. Okay, let's go over this one. So -8. Okay, let's check. So what we have to do here is we have to make sure there's the same base, but then we can set it equal, right? So we have to have the same base. So we know that 25 is 5 squared. So let's set that equal to 5 squared, and that is 3a. It's equal to 5 to the a minus 4. So now we have the same base, right? So if we have the same base on the bottom, then we can set the exponents equal to each other, right? So we have 2 times 3a is equal to a minus 4. So if you multiply this out, right, 6a is equal to a minus 4. So we have 5a is equal to -4. A is equal to -4 over 5. So it is not -8, unfortunately, but uh, it is -4 over 5. Okay, so let's do the last one. That is log of b squared plus 11 is equal to log of -10b plus 2. Okay, so let's start this problem. Also, this class ends at 6 p.m. EST, so like 40 more minutes. Right, so log of b squared plus 11 is equal to log of negative 10b plus 2. So what we can do is, because there's already logs on both sides, what we can do is we can just set the objects equal. So b squared plus 11 is equal to negative 10b plus 2. So from now on, it's quite easy because you all know how to solve a quadratic equation. So it is b squared plus 10b is equal to, no, plus 10b plus 9 is equal to 0. And obviously you factor this, right? b plus 9, b plus 1 is equal to 0. So b obviously is equal to negative 9 and negative 1. Right. So are there any questions on this? If there are no questions, then I will begin the new material today. Also, so today's class, right, is I think the last class before fall break. So next week there will not be a class because of fall break. And then during Thanksgiving week, I think there will also be a break. Okay, so this is also the last class of Unit 6, so it works out quite well. So let's go on to explain some exponential graphs. So what is an exponential graph? An exponential function is in the form of f of x is equal to b to the x, where b is greater than 0 and b does not equal to 1. So when we make a graph, we need to consider the following. The x-intercept. So how do we find the x-intercept? Kaylee, can you help us? How do you find the x-intercept?
You plug in where x is equal to 0.
Not necessarily. That is the y-intercept.
Oh wait, no, I mean when y is equal to 0.
Right, to find the x-intercept, you have to find set y is equal to 0, right? So then, what is this? It is equal to log base b of 0 is equal to x. So this is x is equal to undefined, right? So there is no x-intercept. So it does not intercept the x anywhere, right? So now let's find the y-intercept. And that is just setting the x value equal to 0. So y is equal to b to the 0, y is equal to 1. So obviously we immediately have a point here, which is 0, 1. Again, I've also talked about this point in the past. It is called the reference point because all of the exponential graphs have one, and all of them go over 0, 1. Because when x is equal to 0, anything is equal to 1. So when your exponent is equal to 0, then y is going to be equal to 1. And then we have a horizontal asymptote. Don't forget that we do have this horizontal asymptote, which is here. So because an exponent can never be negative, so there's a horizontal asymptote there, and the graph will look something like this. So because it will never be negative, it will never cross the x-axis. So it'll, as x approaches like negative infinity, the graph will only get closer and closer to the x-axis, but it will never touch. That is the definition of an asymptote, right? This is what the graph looks like. Sometimes you also need some additional points to help you graph. But other than that, here are the following things that you need. This is the x-intercept, the y-intercept, the horizontal asymptote, reference point, and additional points, right? And additional points, you just plug in x values to get the one, just to help shape the graph, right? So here are some properties of exponential functions. Number one is continuous. This means that you can draw the graph without lifting up your utensil, right? So number two is have no sharp corners. So you see this graph, it is very smooth. So when you're drawing a graph, do not make it sharp, right? Make it smooth. So third, it passes through 0, 1, which it does, right? Number four, lies above the x-axis, right? And horizontal asymptote as x goes to plus or minus infinity. Number five, it is a one-to-one function. So remember how to find one-to-one functions? We use the horizontal line test. So we draw an infinite number of horizontal lines, and as you can see, this graph does not intersect a horizontal line twice, right? So it is a one-to-one function, and that does mean that is very important because that means that it has an inverse, which is the log function. So let's go over some properties of exponential graphs. So I think everybody has learned operations on functions. We learned first semester in unit 3, I think. So some operations on functions. Let's see. Our parent graph, let's say, is y is equal to 2 to the x. So it's going to look like this. 0, 1 here. It'll look like this, right? Okay. So how about this? How about y is equal to 2 to the x plus 1? So what happens after that? Who can volunteer? Do I have any volunteers that could tell me what happens to the graph? How about Dan Lu? Dan Lu, can you help?
Okay.
So what happens to the graph when it's y is equal to 2 to the x plus 1 power? How is that different from the first one?
It goes up by 1 unit.
Not necessarily, because this is in a parentheses. That means it affects the x. It affects the domain, not the range.
Oh,
So
I didn't see that. It moves to the left by 1 unit.
yes, that is true. So a lot of times when you have operations on functions, it is good to note the reference point. That is where it is. That is where the most important things are. So the reference point is going to move to the left by 1 unit, and naturally, the other components of the graph shift accordingly as well. So let's look at some other operations that are here and what they look like. So let's look at this. Let me see. Number 3 here is y is equal to 2 to the x minus 1. So what happens here is the whole graph, right? Now, to the x minus 1, this affects the range. So this graph will move down. So that also means that the reference point is moved from 0, 1 to 0, 0. The horizontal asymptote is also moved down by 1 here. It's moved down by 1. And the graph is going to shift accordingly, like so. So that is y is equal to 2x minus 1. Now, another one here is y is equal to 2 to the negative x. So again, this affects domain. So this affects domain. That means we are reflecting about the y-axis. So that means our reference point is still 0, 1. However, you're starting from here. You're starting from here, and the graph is going to look like this. Now we have, let's say we have a vertical stretch. So y is equal to 2 to the 3x. So the reference point is still the same at 0, 1. But see, the graph is much taller now because you stretch it vertically by 3. Right. And finally, we have something like this. Y is equal to 2 to the 4 minus x. And that is, we have two operations, actually. So if you rewrite this, negative x plus 4, here we need to shift horizontally, and then we reflect. So we shift to the left by 4 units, and then we reflect. So if you shift to the left by 4 units, then our reference point is what? It is negative 4, 1, right? So negative 4, 1, and then if you then reflect it, it's just positive 4, 1. So it's going to be like here. So let's see. It will be like this. Okay. So these are the operations of the exponential function. So hopefully you took notes on this, and then let's move on to the logarithms. So logarithms, despite looking a bit complicated, are very simple and very similar to exponents. So let's look at what a logarithm function is. A logarithm function is f of x is equal to log b of x, where b is greater than 0 and b does not equal to 1. Right, so if you look at the graph here, an exponential function would be like this. So does everybody remember when you have an inverse, you reflect the graph over the line of y is equal to x? So the logarithm graph will look like this. The reference point is not 0, 1 anymore, it is 1, 0. Because whenever x is 1, then it has to be 0, right? Because anything to the exponent of 0 is equal to 1. So it has to be 0. So then we have something like this. Instead of a horizontal asymptote, we now have a vertical asymptote here. See this vertical asymptote. Right, so also pay attention to this vertical asymptote because it is also very important. So let's look at some things that you also need to take note, which is the x-intercept. So for both of them, you need to look at the x-intercept, y-intercept, horizontal, asymptote, reference point, and additional points. Okay. And some properties is it is continuous, no sharp corners, it passes through 1, 0, with vertical asymptote, and it is 1 to 1, which means that it has the inverse again. So basically the same things as the exponential function. So now let's go on to some operations on log functions. Okay. So let's see. Let's see what's happening here. We have what? Let's just say the first one, our parent is y is equal to log base 2 of x. That's going to look something like this. Right. So now let's look at y is equal to log base 2 of x plus 1. See this one, what you have to do is you have to shift to the left. So that means the reference point is going to be 0, 0. That also means that the asymptote, vertical asymptote, is also shifted. So it's like this. Now let's go on to another one. So let's do y is equal to log base 2 of x plus 1. So since it is not in the parentheses with x this time is outside of the function, this actually affects the range. So that means it is going up or down. Right. That means the reference point will go up. That is 1, 1. Vertical asymptote does not change. So one of the most important things you have to do when you're graphing is the reference point. Now we have log base 2 of negative x. This is what? We reflect about the y-axis, right? So we reflect about the y-axis. So we see our parent graph here. Our reference point is now negative 1, 0. Vertical asymptote is essentially the same. Like this. Now we have some different things like y is equal to negative log base 2 of x. So this is actually a vertical inflection here. So there's the same vertical asymptote, and the reference point is still the same, except it is going down like this. And we have one more, negative 2 log base 2 of x plus 1. This one is a two-step problem. So we still have the same vertical asymptote because there is no domain change, but it is all a y change. So we have to stretch. We are stretching vertically first and also reflecting, and then we add 1. So the reference point is 1, 1 here, and something like this. Right? The difference is visible. So the point is that you need to make sure you have the asymptote, additional points. I didn't include any additional points right now, but because we really don't need them. Include asymptote, the reference point, and at least make the graph presentable, right? So I can see the difference. Otherwise, there's no need to get it too exact. Okay. Now let's go over some examples. So I'll give you 5 minutes to do this, and then I will come back and check. Okay, so let's go over this. Y is equal to 4 times 2 to the x plus 1. So I hope everybody had a chance to graph this in their notebook. So let us begin this problem. So the base obviously is 2, but that doesn't matter that much. So we have our reference point at what? It is 0, 1. So usually we have a reference point at 0, 1. So let's see how that changes. First of all, what we have to do is we have to stretch this vertically by a factor of 4. So that is no problem. We can just make it skinnier, right? And then we add 1 to the range, which is basically moving it up by 1, right? So now the horizontal asymptote becomes y is equal to 1. And the reference point is now 0, 2. So we have this. And it's a very steep graph because we vertically stretch it. So it is very steep. If you want to be more accurate, you can put some additional points, but I'm just too lazy to do that. So let's do number 2. This is a log graph this time. Okay, so let's start this problem. So of course the base is 2 again. So we have a reference point. We have a reference point at 1, 0, usually. But in this case, we actually move right and then move down. So we have a reference point here, actually, which is 2, -1, because we moved down. Vertical asymptote is still the same. Right, so we have this. And the reference point is moved right and then down. Okay, so I think that is all for today. Yes, short class. We didn't have much to cover, just the graphs. So I hope everybody has a great fall break. And I'll see you next time. So remember, next week does not have class, right? So next week, I'll see you.